Welcome to the Essential Biomechanics podcast. This is your place to listen to the most important topics in orthodontic biomechanics. Let's get started with your host, Professor Gustavo Gameiro.
Hello everyone, I'm Gustavo Gameiro, and it's my pleasure to share with you my first podcast about the book The 10 Fundamental Concepts of Biomechanics. Basically, I would say that the concepts presented in this ebook, which you can download for free from my website or social medias, constitute the foundations of our clinical practice. If you apply the knowledge of scientific biomechanics in your clinical routine, the quality of your treatments will improve, and you will work much more efficiently. Fundament number 10. Never underestimate the influence of the exact laws of physics in your clinical practice. Equilibrium in clinical practice. How to apply this knowledge clinically? The answer to this question requires a more in-depth study of the subject. But the understanding of the principle of equilibrium represents one of the first steps for the rational and effective application of biomechanical principles in orthodontic clinic. The beginner may even classify this knowledge as too theoretical and complex, although it forms the basis for understanding how the appliances work. Applying the theory of equilibrium in the day-to-day clinical practice will bring innumerable positive surprise to the professional. You will be able to simulate and predict the desired dental movements in order to select and build the appliance with more consistent force systems. You will notice that sometimes some movements are scientifically impossible to realize with just one device or activation, because we will never be able to disrespect the laws of physics. For example, we cannot create an appliance that is not in equilibrium. In addition, you will be able to assess the actual needs of anchorage control in order to minimize undesirable side effects, while potentiating the desired movements. The basic line of reasoning. Basically, this final chapter will help you to develop a line of reasoning for the choice and activation of most orthodontic appliances inserted between two teeth or specific groups of teeth. It's therefore a reasoning used especially for the application of segmented arch techniques, which are those that divide the dental arch into an active unit, represented by the teeth that you want to move, and a reactive unit, represented by the anchoring teeth which we normally do not want to move. Only with the resources of these techniques, we will be able to precisely define the direction of the desired and undesired forces of our orthodontic mechanics. This biomechanical approach is called force-driven orthodontics. Differently from the shape-driven orthodontics, focused on the wire's shape, the force-driven orthodontics emphasize principles and force systems. After all, who is driving the bus? This is a common expression used by Professor Bert Milsen. Force-driven orthodontics, the statically determinate and indeterminate systems. The detailed management of the immutable possibilities for applying controlled force systems to move teeth is beyond the scope of this ebook. However, we consider important to provide a brief overview of some important characteristics of the two types of biomechanical systems. Please see the following. Statically determinate appliance. Appliance in which the law of equilibrium allows us to estimate all the forces and moments acting on the wires and teeth. The main example of this system is the cantilever, which will apply only one force at the end to which it's connected, while at the other end, inserted into a tube or bracket, both a force and a moment will be produced. The planning of movements with this type of appliance is quite simple, since the use of a tensiometer and a ruler will give you all the information about the forces and moments that will be applied in the active and reactive units. Statically indeterminate appliance. Appliance in which we cannot estimate all the forces and moments involved simply by applying the equilibrium formulas. In this type of system, a wire is inserted into two or more brackets or tubes. In this category, we can include most orthodontic appliances, such as continuous and segmented leveling arcs, retraction loops, rectangular loops, roof springs, transpalatal bars, and lingual arcs. The planning of movements with this type of appliance can be very complex in some cases. In this book, we will only emphasize that the principles of equilibrium and the 6 geometries constitute the most fundamental topics for understanding these systems. We have a lot of videos about these principles in our YouTube channel. Certainly they will help you to understand this topic. Let's now see the 5 steps of a force-driven planning. This chapter will demonstrate how to elaborate a force-driven planning. You will realize that this biomechanical planning can be used whenever you need to carry out a specific and controlled movement. This type of movement is the one in which the application of specific forces is planned by you according to the malocclusion that you want to correct. I'm sure that this knowledge will change your way of facing orthodontics, making it easy to solve the many complex cases routinely found in our practice. These steps can be applied to solve malocclusions in the 3 planes of space: transversal, occlusal, or sagittal. Let's see one example in each plane so you can practice the application of the 5 steps. The 5 steps are: number 1, identify the problem to be corrected. Number 2, check if your free body diagram is in equilibrium. Step number 3, select the appliance to solve the problem. In step number 4, you need to activate the appliance to get the desired force system. And finally, in step number 5, you will evaluate the possible need of reactivations. Remember that the free body diagram of deactivation forces should attend the principle of equilibrium, because it is based always on the appliance equilibrium condition. Let's see some examples. Problem 1. The second upper molar excessively inclined for the buccal side. The chief complaint in this case was that the patient was chewing the cheek. Let's follow the 5 steps. In this first case, an occlusal view is used for planning the movements. It's very important, however, to be aware that significant changes can also occur in other planes, depending on the case evaluated. Step number 1, identify the problem to be corrected. We can perceive the excessive buccal inclination of the upper second molar in both occlusal and frontal views. In this case, the simplest and most effective solution would be the application of a single lingual force in this tooth. In this first step, you only need to draw the needed forces to correct the problem. In this first step, different professionals usually agree about the most appropriate solution for the case. In the next steps, however, there are countless varied approaches to deal with the same problem. In step number 2, we will check if our free body diagram attends the principle of equilibrium. Before taking a pen in order to draw a diagram, you may think, come on, this is a very small problem. Let's bound a tube at the molars, let's insert a straight wire and see what happens. In this case, if you use a straight wire, it would not provide the force you have planned. The relationship between the molars creates a class 1 geometry force system, as you can see in this figure B. Note the application of undesired force systems at both the first and second molars. This system is considered therefore inconsistent. Here the tooth rotations were exaggerated for illustration purposes. You definitely should draw a free body diagram. You will be able to look for a consistent system. At the same time, possible inconsistencies can be checked, contributing for a proper anchorage selection. Let's come back to our case. Let's draw a deactivation diagram based on our desired force, as you can see in this figure A. If we apply a single lingual force at the active unit, naturally, a buccal deactivation force will be applied at the reactive unit. Moreover, this unit will also perceive a moment in the opposite direction of the moment related to the two previous forces. The deactivation force diagram in this figure B is compatible with your planned force and is consistent regarding the active unit. This free body diagram, as you can see in figure B, is correct because it attends the principle of equilibrium. Moreover, it demonstrates a potential side effect associated with the inconsistent force system applied at the reactive unit. Step number 3, you select the appliance to solve the problem. Considering that, in the present case, only a single force was required, a cantilever inserted into the first molar tube and ligated in some accessory, it can be a bracket, a tube, or a button, on the second molar was selected. The main characteristic of this system is its high degree of qualitative constancy. I mean a relatively constant moment-force ratio, which means that the system maintains the directions and proportions of its forces and moments during the deactivations. This results in a more homogeneous and predictable orthodontic movement. In step number 4, we need to activate the appliance to get the desired force system. There are infinite possibilities of configurations for the cantilevers. We can incorporate bends and curvatures into the cantilever in order to change the line of action of the resulting force, and thus obtain the desired force system for a specific orthodontic movement. They are usually made with titanium molybdenum wires. Basically, the cantilever activation is made following a rule of thumb. Make a deactivation shape, as you can see here in green in this picture, by which a line between the points of ligation from the deactivation to the activated shape will establish the desired line of action. The desired line of action in this figure is illustrated by the black traced line. Finally, in step 5, we will evaluate the possible need of reactivations. As previously mentioned, the cantilevers present a high degree of qualitative constancy, keeping the directions and proportions of its forces and moments during the deactivation. In some cases, as in the present one, no reactivation was needed. The deactivation diagram and the results after a few months you can see in these pictures. Pay attention that only the desired tooth was moved. In this case, the force and moment in the reactive unit were not desired. So, we have used an extensive anchorage unit composed of two posterior segments joined by a transpalatal bar. Problem 2. Second lower molars excessively angulated for the mesial side. The chief complaint in this case, the black spaces in the mouth. Let's follow the 5 steps again, focusing on the process of molars uprighting, a very common situation in adult orthodontics. Step 1. Identify the problem to be corrected. Our ideal system of force for this molar would be the application of only a counterclockwise moment. We do not want any extrusive or intrusive force on this tooth. Step 2. Check if your free body diagram is in equilibrium. If we apply a moment in the active unit, in blue in this figure, we know by the law of equilibrium that a moment in the opposite direction in the anchorage unit, in gray in this example, will be generated. So this diagram was a piece of cake. In this case, our anchorage unit will be formed by the 10 lower teeth, from premolar to premolar, conjugated with a rigid steel arch. This will minimize the undesired moment in the anchorage unit. In step number 3, we will select the appliance to solve the problem. Whenever you wish to exclusively apply moments by using only one appliance, this system will certainly be statically indeterminate. That is, it will be an appliance whose ends will be fully inserted into two teeth or group of teeth, in both the active and reactive units. A good choice for this case is a roof spring, a segment of wire, usually a TMA wire, which is initially made passive, with one end attached to the auxiliary tube of the molar that we want to move, and the other end will be inserted into a cross tube adapted between the canine and first premolar, for example. In step number 4, we need to activate the appliance to get the desired force system. The roof spring was activated in this case by making two V-bands near each insertion site. This activation is made in the principle of the truncated V-bands. The angulation of the bands, around 40 degrees each, was equal in both extremities based on the arms of the spring starting at a passive angle. In step number 5, we will evaluate the possible need of reactivations. The reactivations using statically indeterminate systems are more complex and require more rigorous clinical control than the statically determinate appliance. That is, when the patient returns 1 month after you have installed your appliance, your activation has probably changed. Yes, you cannot forget that your teeth will move with your activations. In our example, imagine that your molar rotated a few degrees while the reactive unit held its position because it was anchored. In this case, the movement of the active unit has already changed the configuration of the force systems. Of course, the activation was specific to the teeth positioned before moving. When dental positions change, the force systems also change. As a practical tip, whenever you use a statically indeterminate appliance to produce equal couples, a class 6 geometry force system in this case, it's best to reactivate it monthly, because the activations quickly cause changes in the system of force during tooth movement. In our example, roof springs were installed on both sides of the patient, and the two molars were uprighted at an impressive speed. Since the correct force system was applied, this is an example of force-driven orthodontics. We have applied the specific force systems for solving the problems. After the uprighting processes, we used a shoehorn loop to close the space. And since these were not very large, the control of the anterior anchorage was made only with torque control to avoid the inclination of the anterior teeth to the lingual. As a clinical tip, for the mesialization of posterior teeth with greater need for anterior anchorage control, we suggest the use of mandibular protractor, for example, a power scope appliance, for this purpose. If you want to see this clinical tip in a video, please check an example of this simulation in the description of this video. Problem 3. Upper left segment excessively inclined for the buccal side, the so-called scissor bite. The chief complaint in this case was the difficult chewing on the left side. This last case is more complicated than the previous ones. But let's follow the 5 steps again, focusing on the asymmetrical constriction, where the left upper side requires lingual tipping. I hope you can see how the use of an appropriate system of force can work in our favor to obtain controlled dental movements. Step 1. Identify the problem to be corrected. Although there are many solutions for this case, the presented approach has used a combination of contraction with third-order activations, or torques, to obtain a unilateral contraction of the upper arch. The reason for this approach has not only mechanical goals, but also biological ones. The asymmetrical movement can be achieved by the application of differential moments. That is, this concept is based on the fact that tipping movements occur much more rapidly than translational movements. In this case, a finite element analysis showing the tooth displacements and radial strains on the periodontal ligament induced by asymmetrical activation of a transpalatal arch. The red force in this picture will represent the desired force systems, and I will explain why this force system is a good one for this case. When a simple force is applied, to the crown of a tooth, the stresses and strains on the periodontal ligament will be significant in some areas, which favors the action of bone cells responsible for orthodontic movement, the left side in this picture. On the other hand, if we apply the same force to a tooth at the same time that we add a moment to obtain a translational movement, the strain values of the periodontal ligament are much lower, minimizing the cellular reactions responsible for the movement in the right side of this case. So in this case, we will potentialize the movement of the left side. The forces and moments in red in this picture represent the planned force system for this case. In step number 2, we can check if our free body diagram is in equilibrium. As you can see in this picture, the diagram is not in equilibrium. Let's draw a correct free body diagram. In order to make the desired force system feasible, the undesirable but inevitable vertical forces will be generated with this type of activation. Now we have a correct free body diagram in equilibrium. The major side effect in this case is the vertical extrusive force. Depending on the patient's masticatory forces and facial pattern, this force can be problematic. As a clinical tip, the application of occlusal splints can reinforce the anchorage on the side we do not want to move, the right side in this example. Applying the splint on this side, we will also avoid the occlusal contacts on the side on which we want to make the movement. In this way, the desired movement will be optimized as it's occurring in a region free of any interference. If you want to learn more about this clinical tip, check the video occlusal splint in the description. Let's continue with step number 3, select the appliance to solve the problem. The combination of contraction forces with the desired differential moments was obtained by an asymmetrically activated transpalatal arch, made with a 0.8 mm stainless steel wire to reduce its load deflection range. Step number 4, the activation of the appliance to get the desired force system. The TPA was constricted and the lingual roof torque was applied only on the right side. This unilateral torque generates a system of force similar to a class 3 geometry force system at the tubes. The equivalent force system at the center of resistance determines the resultant asymmetrical movements. You can see that the resultant force system at the CR of the left side will generate a tipping movement in these sides, while in the right side the translational movement will be stimulated. Number 5, evaluate the possible need of reactivations. As mentioned before, a careful clinical monitoring is strongly recommended when using statically indeterminate appliance, such as the transpalatal arch. In the present case, the selected activation could keep a constant moment-force ratio throughout the correction of the scissor bite, since the applied force system has a large range of deactivation. Once the scissor bite is corrected, the transpalatal arch can be either inactivated to avoid undesirable movements or reactivated according to the needs of the case. If you want to see more details about this case, please check the video Scissor Bite in the description. Dear friends, this was the last episode of this podcast series. I hope you have enjoyed listening to the 10 fundamental concepts of biomechanics. In the next days, I'm planning to organize a list of all the episodes into downloadable files so you can listen and study again and again whenever you need. I truly believe that these fundamental concepts can help you understand how the appliance works independently of the technique you prefer or use. You will be able to understand all of them. I also invite you to check out my new book, The Secrets of Biomechanics. If you really want to go deep into scientific biomechanics, this book has all the details you need to learn in order to work with the man-segmented arch techniques. If you have any questions about my books, please get in contact directly with me. It will be my pleasure to answer you. My wish is that biomechanics will always be with you.